Okay, in class today we're talking about finding volumes from different cross sections. Okay, so once again we're going to be given a graph of things. Okay, maybe this is a solo graph like this or something, I don't know. Okay, and we're going to find, of course, the area from our intervals. Usually the intervals are x-axis intervals, unless, of course, we're finding a y-axis formula. So we're going to find the area underneath this curve and the x-axis. Okay, so we've been doing that. We do that by taking the interval, I guess this is f of x. Right? We'll find the area under that curve, which we're going to call r just for fun. So r is the interval from a to b of the whatever function that happens to be. Okay? So that is an area. So what they're going to tell us to do is now we're going to take this area and we're going to build. Okay, we bought our, this is like a Monopoly, you bought Park Place, it's a flat game board, and now we're going to start building hotels on it. Because in Monopoly, the more hotels you have, the more the person has to pay you when they land on your property. Okay, so imagine this is going to be a three-dimensional. So three-dimensional, here's your y-axis, this is your x-axis, and of course, this is your vertical z-axis. Okay, so if you can imagine, this is the graph of r that we just did. Okay, on a three-dimensional plane. Okay, we still have the interval from a to b, so here's your a, right? Here's a on the x-axis, and this was about here is your b. So what we're going to do is we're going to build rectangles and triangles and semicircles and squares and find different areas of these things. Okay, so if I were to build a square has the same height as it has base. Okay, so this is going to be the base, which we're going to call S, the side length of your square. Okay, so if we were going to make a square, we would have to come up the exact same amount, right? And because it's three dimensions, it kind of looks like a parallelogram. But this, you can imagine this is the area, or rather the volume, well, I guess the area of a square. Okay? And as, of course, we get wider, your squares get taller, right? Because your side length is now wider. And as we get more narrow, your squares are not as tall. Okay, so we have a whole bunch of these squares, and if we take an infinite amount of squares, we can add them together and basically get a volume, right? A volume of whatever's in three dimensions that looks something like that. Okay? So what we're going to do, of course, is we're going to find the area of this square, and we're going to take the integral, and that's going to be our volume. Okay? So the area, or rather the side length of our square is the distance between, that's not how you spell between, your two curves. Okay, in other words, this is the curve, your y equals 0 or your x-axis, and then we have that other curve which we called f. Okay, so that is the side length. The distance between your two curves is the side length. Okay, so then how do we find the area of one of these squares? Right, base times height, so s times s or s squared. Okay, and for our function, which I called f, right, that's this length. The y value, of course, for any given x is given to you by the y value for that given f, or f of x. So what we're going to end up doing is this is equal to the function squared. Okay, so whatever the distance is between your two curves, that is the side length. And in this case, this distance is given to you by the y value from your function, which is just f of x. Right? The y value at any given x. Okay, so if we're going to take the volume, that's the interval from a to b of your side length, which is given to you by your y value, right, from your function, squared. Dx. Okay, and that's how we're going to find the volume. If we have a bunch of squares, right, so you have a bunch of squares, that's going to be the formula. And of course, depending on whatever your problem is, this is going to change. Right? If that were a linear function, maybe it would be like a 2x minus 5. right? That's going to be your function that you're squaring. Or maybe it's a quadratic, an x squared, and you're going to square that function, okay, on whatever interval it happens to be. Okay, so what if we're given something other than squares? Like maybe we want to do semicircles. Or potentially, let's do rectangles first. Okay, so let's do rectangles. Here I'm going to draw your picture again, right, in 3 dimensions. So here's your y-axis in 3 dimensions. Here's your x-axis in 3 dimensions. And here's your z-axis. Okay, so let's think about the graph of y equals root x maybe, okay, which is something that looks like this. Right, that's the root x graph. Okay, so maybe we're going to use rectangles whose height is twice the base. Okay, so we're going to come in here and we're going to have your interval, right? So we're going to go from A to B, whatever it happens to be, from A to B, and we're going to draw rectangles whose height is twice the base. So if this is my first rectangle, my height is twice as big as that first rectangle. Okay, so as I make more and more rectangles, these things are going to get taller and taller, right? Because my y values are getting bigger and bigger as I go more and more to the x. Okay, so we're finding the volume of this thing. Okay, basically it looks like a, I don't know, sort of like a square root graph, right, in 3 dimensions, with a bunch of these rectangles whose height is twice the base. So the height of this is the y value from your function, right? The distance between the x-axis and your graph is the y value. So then the height is going to be twice the y value. Okay? So the area for your rectangle is base times height, which is y times 2y, which has a total area of 2y squared. Okay, or if we're going to write this in general, twice your function squared, right? In this case, y is the y value, also known as f of x. So if we're going to find the volume, once again, the volume of our thing goes from A to B of 2 f of x squared dx. Okay, and because of our rules of integrals, we can take your constant and move it to the front. Okay, so this is 2 times the integral from A to B of your function squared. Okay, which looks an awful lot like your square one, right? Your square was just the interval from A to B of the function itself squared. But now we have this extra multiplier because your side lengths aren't the same. Your side lengths are now, one is twice as big as the other one. Okay, and it turns out that that's always going to be the case. Every time we change our shape of your cross section, we're going to change the coefficient of the integral. Okay, so let's think about a semicircle, right? Let's think about semicircles. Okay, so here's your y-axis, here's your x-axis, here's your z-axis. Okay, so maybe this is our graph again, something random, and we're going to draw semicircles. Okay, so here's A and here's your B. There's your interval. So we're going to draw a bunch of semicircles in here. Okay, if I have a more narrow distance, then I have skinnier semicircles, and when I have a longer distance, I have taller semicircles. Okay, so this is going to look like some type of a saddle thing, right? It has 3 dimensions. Maybe you can envision it. I don't know. It's kind of hard to see, of course, but we have a semicircle. Remember, this is the length from here to here is the function evaluated at x. Okay, also known as your y value. Okay, so from the x-axis to your function is the y value, aka f of x. Okay, so if we're looking at your semicircle, right? The area of a semicircle is half of pi r squared, right? Half of pi radius squared, where only this much is your radius, right? So how does your radius compare to the whole entire y value? Radius is half of your y value. Okay, so I'm going to replace r with my function, right? And this is going to be a function when it comes down to the math, right? Like a quadratic or maybe even a trig function, right? It could be the r is half of your functional height, right? Half of the y value. So this becomes 1/2 of pi times half of f of x squared. Okay? So we still have half of pi. Now what happens when I square 1/2? That becomes a 1/4 because a half times a half is a fourth. And then I have f of x squared. Right, so then what is the coefficient here? It's 1/2 times 1/4, which is 1/8, right? So 1/2 out front. This is the same 1/2. 1/2 times 1/4 is 1/8. I still have my pi, and now I have f of x squared. Okay? So notice what all of these functions have in common. They all have an x squared term, right? And they all have the squaring of the function. Every one of them. Every time we find an area, you would expect to have something being squared, because area is a squared unit, so you should have a squared something or other in your area. So if I'm finding the volume, right, that's 1/8 of pi times the function squared dx. And once again, I can take my coefficient and move it to the front. Okay, so the volume is the 1/8 of pi times the integral from a to b of your function squared. Okay, so no matter what's going to happen here when we're finding the area of a cross section, you always have that interval or the integral of your function squared times some type of a leading coefficient, right? And the leading coefficient is based upon the shape that you are trying to find the areas of. Okay, so squares don't have any leading coefficients. Rectangles have whatever the ratio is of your side length to your base. Here we have semicircles, which have a 1/8 pi coefficient. Okay, so anytime you're finding the cross-sectional area, it's a coefficient times the integral of your function squared. Okay? Yeah. So let's look at some problems involving, well, maybe a little bit more math than what we've been doing so far. I'll be right back. Okay, so here's the worksheet that my classmates have here, my students. So here we have a region. This line is y equals natural log. Okay, so this is your natural log function. Hopefully you recognize this as a natural log function.
I did not. I saw it.
Okay, it has an intercept at 1, 0. So there's natural log of x. And then this is your linear y equals x minus 2. Okay, so if we're going to find the volume of a solid that is formed where the cross sections are semicircles, right? Semicircles. So we're looking for the volume. Semicircles had a pi over 8 as the coefficient. Okay, pi over 8 was the coefficient that we're going to have outside of our interval. Right? That's what we're multiplying by for every semicircle we ever have. Okay, it's always going to be a pi over 8 times the interval of the top function, right? Because the distance here in between your things is the top function minus the bottom function. So natural log x minus 2. Okay, and we're going to square that function, right? Because it's always side squared or radius squared or whatever squared. Okay, now the only thing we have to do is figure out our interval, right? So we're going to go to our calculator and we're going to use the intersection button to figure out what my lower bound and my upper bound are for my intervals, right? My limits of integration. Okay, so we're going to do this on a calculator. There's lots of calculators that you can use. You can use Desmos or various other things. So I'm going to pause the video and do this. And when I come back, you're going to see the limits of integration. Okay, so using the analyze graph function and finding the intersection, we found a left intersection of 0.159 and a right intersection of 3.146. Okay, so you have to use your calculator, or you could set these equations equal. Heaven forbid you want to actually solve where the natural log of x equals x minus 2, right? But completely possible to do that. It's easier if you use a graphing device, a calculating device. Okay, so now you put this whole thing into your calculator, and it will tell you the volume of that where you have semicircles as the cross-sectional area. So 0.607 is what my calculator told me the answer was, and our units are cubic, right? Cubic units because it's a volume. We're finding a volume, so the volume are cubic units. Okay, so the next one says find the volume with square cross sections. Okay, so for squares, we don't have a coefficient. It's just the distance in between your two things squared using the same interval from 0.159 to 3.146 of natural log x minus x plus 2 squared dx. Okay, a square does not have a coefficient in front of the integral, and we get 1.545 cubic units when you plug that into your calculator. Okay, so if you remember that all of these volumes are found by taking the side length and squaring it, and then multiplying it by a coefficient depending on what the shape is, right? These problems are not very difficult. Just remember what shape it is that you are finding the volume for. Okay, so here we have another one, right, where we have two functions, and it has 2 points of intersection. So once again, we're going to use our calculator to figure out what this intersection point is, right? So we have A at 0 and then B, and then we're going to use our calculator and figure out what this one is also. Okay, so we're going to have two sections, right? We do two sections because here we have the g of x minus f of x, right? G is on top for this interval. And then for our second interval, the f function is on top. So we're going to do some practice with our calculator figuring out what these points of intersection are so we can set up our integrals and find the volumes. So because we have squares, right, we don't have a coefficient on either one of these volumes. So first I'm finding r, right, which has the g function on top minus the f function, okay, squared, because it's a square. And then I have a second interval where the f function is on top and the g function is below. So I have two intervals. I found 0.178 as the first intersection, and I found 1 as the second intersection.
Wait, doesn't it go from 0?
Okay, so these are the two functions that you'll use to find the volume if we have squares. Okay, now down here we have equilateral triangles. Okay, and if you remember from an equilateral triangle, probably not, but the area is the side squared times the square root of 3 over 4. Okay, that's using special right triangles to figure out the area of this equilateral right triangle. Okay, so the volume for this is going to be root 3 over 4 as the coefficient. Okay, and then I'm just going to do those same intervals of the same thing plus the other one. For just S, sorry, my students just corrected me, which is great. So I don't need the R one. I don't need from 0. I just need from 0.178. So 1 of this function. That goes there. Okay, and that would give us the volume if we had equilateral triangles. Okay, so just commit this formula to memory for equilateral triangles. Okay, so that's how we find the cross-sectional, or I guess volume with different cross-sectional areas. Hopefully this helps and you feel smarter.